In today's video, we will be covering what is binary search, how to write a binary search, what are the three types of binary search. Yes, there are multiple types of binary search, and when to use what type of binary search. Finally, we're going to go through everything with some sample questions. This will be a long video, but by the end of it, you will know binary search very, very well. Now, what is binary search? Binary search is an efficient algorithm for finding an item from a sorted list of items. So over here, we have a sorted list and we want to find the item 21. In this case, we can use binary search. When do you use binary search? Like I mentioned, binary search is used when you have a sorted list and you need to find a target. So if a question mentions something like, oh, we have a sorted array, or the numbers are in increasing order, and you want to find a certain target, that is when you know you need to use binary search. How does binary search work? It works by repeatedly dividing in half the proportion of the list that could contain the items, until the item is found or proof that the item does not exist in the list. The basic idea is to compare the middle element to the target item. If the middle element is equal to the target item, we have found the item and we return. If the target item is less than the middle element, then we continue searching in the left half of the array. If the target item is greater than the middle element, then we will search in the right half of the array. The process continues until the target item is found or it's clear that the target is not in the list. I think the concept is a lot easier to understand when you see it in person, right? Say we have an array of sorted numbers and we want to find 19 over here. So like I said, we're going to first find the middle element. We have low and our high, and we see that 60 is way bigger than 19. That means the 19 must be in the left side of the array. So in the next step, we search through the left side of the array. The middle element is 22. 22 is still bigger than 19, so we know it's left side of 22. In the next step, we go here to the left side of 22. We see that 14, the middle element, is a little bit smaller than 19. So that means it must be on the right side of 14. So next step, we come to 19 and we found the index 2. That's where our target element is at. Notice how each time the array is being divided by half. First time was 3 to 99, right? But immediately it becomes reduced by half from 3 to 60 and then 3 to 22. So that is why this algorithm is so efficient. Each time the search space is reduced by half. What is the runtime of binary search, or how fast is binary search? Since we have the array and we are constantly dividing it by half, which is dividing it by 2, log in computer science is base 2 instead of base 10. Therefore, our runtime is log n. What exactly does log base 2 of n mean, right? In math, we learned the formula if y equals b to the power of x, then we have x equals to log b to y. In our situation, n, the number of elements in our array, equals 2 to the power of x. X is the calculation of the runtime, i.e. the number of operations. When we have an algorithm, we want x to be as small as possible. Log 2n is very efficient. When we have log 2 of 7, it's only 2.8. When we have log 2 of 1000, it's only 9.9. What this means is that if you have 7 elements in an array, it will roughly take 3 operations to complete it. Whereas if you have 1000, it will only roughly take 10 operations to complete it. To help you better understand how fast binary search is, say you have 1 to 1000, right? If you just want to find 1000 by counting, then you go 1, 2, 3, 4, 5, 6, 7, 8. You basically need to process every element once. Therefore, the runtime is on, which is 1000. You have to count all 1000 of them to reach your target. With binary search, since we're constantly dividing the space by half, the runtime is only log base 2 of 1000. That is only 9, or like close to 10 operations. That is extremely fast compared to 1000, and this gap will only get bigger as n increases. Take a look at this big old chart, right? As input size gets on, the gap between on algorithm and log n algorithm will continue to increase. This means that log n algorithm will be a lot faster than on algorithm as the space or size of the array increases. Let's run through an example of binary search together. Basically, in this question, we're given a set of numbers that are in increasing order, and we're given a target. We need to return the index of the target. If the target does not exist, we return -1. So over here, we have an example of a sorted array. The target is 9, so the index is 0, 1, 2, 3, 4, 4, and here's the output, 4. In this example, again, same array, but the target is 2. Since 2 does not exist, we return -1. First, we initialize the left and right index. We create a while loop that runs while the left index is smaller or equal to the right index. For every iteration, we find the middle index. Here, it's important to note that this is an integer division, and the default behavior is to get the floor of the value. I'll explain why this is relevant when we talk about the two other types of binary search. For each iteration, we check if the middle index of the nums equals to the target. If this is a match, then we found our target and return the middle index. Otherwise, say if the middle index is smaller than the target value, right? Then we know that we want to loop through the right side of the array. In this case, we set the index I, the left index, from left to middle value +1. We do a +1 because we know that middle index is smaller than the target, so it can't be the middle index. So it has to be anywhere from middle +1 to the end of the array. Otherwise, say if the middle index is greater than the target value, then we set j, the right index, to be middle -1. What this means is that the next iteration we will search through the left side of the array, I to middle -1. In case you didn't understand, I'll explain it one more time, okay? So over here, if our number of middle index equals to the target, we have found the target and we return the middle index. But if we have not found the target yet, the middle index number is smaller than the target. So over here, you can see that the middle index number 50 is smaller than the target 68. Then we know that 68 cannot be over here. It must be on the right side of the array, right? So what we would do is move the lower index to middle +1, because we know it's not middle. So it has to be middle +1 to the end. And that's what we do here. See, middle +1 to the end. So that's what we're doing here. On the opposite example, say the middle index is greater than our target, right? You can see here 30 is greater than 11, so it must be on the left side of the array. And since we already checked middle, it has to be from middle -1 to the starting point, right? So that's what we're doing here on the second part, where we are setting the left high to middle -1, right? That's what we're doing over here. See? Let's imagine this. What if the array contains duplicates, right? What if it contains duplicates and you want to find the target 4? Do you return this one? Do you return this one? Or do you return this one? For some specific situations, you actually need to find the leftmost or minimum index, or you need to find the maximum, the rightmost index. In this case, we simply modify our binary search a little bit. Say if we want to find the left bound or the minimum index of the target number, right? Instead of saying if the number equals to the target, we will immediately return it. We will say that if the number equals to the target, right? It equals to the target and the number next to it is not the target, then we return the middle index. This works because, like, imagine you landed here, right? If this is equals to the target, there can still be a number left of it that equals to the target as well. However, if you confirm that the number next to it is not the target, then it's guaranteed that the current index is the left bound. So over here 4, the left is 3, which is not the target. This is the left bound. Here 4, left of it is still 4, so this is not the left bound. For the right bound, we simply just do the same, right? Check if there's anything to the right. If there is, make sure it's not the target. Let's do an example here. This question is called find first and last position of element in sorted array. When you see find position and sorted array, it should immediately hit you that you should use binary search. Just as I described before, we want to find the left bound and the right bound. So here the target is 8, right? In this array we have 2. The left bound is index 3, 0, 1, 2, 3, and the right bound is index 4. So as a result, we return 3 and 4. In the second example, we have target 6. Unfortunately, there's no 6, so we return -1 and -1. Last example, if empty array, we also return -1, -1. Let's first take a look at the binary search for the left bound, right? This is exactly the same as the binary search I showed before, except for the middle case, we have an extended if statement. Here we're saying that when the current number, like the middle index number, equals target, we do another check. So say over here, right, we want to find the leftmost bound. We land it here. We want to check that, hey, this equals to target, but is this the leftmost bound? How do we know? We know that this is the leftmost bound if mid equals 0 or nums mid -1. So if we're here, then this would be nums mid -1 doesn't equal to target. So even though we're here, the current number equals to target, but because this number next to it equals to target, this statement won't pass. So we will skip, we'll run to the next iteration. And since this equals to the target, it wouldn't be here. We would land over here, where we adjust j, the left bound, to become mid -1. So after this iteration, the left bound will become middle -1, which is here, this index. What we're essentially doing here is checking if there's anything on the left. If there's things on the left, we let binary search continue to run on the left part of the array. Well, why do we check mid equals 0 or mid -1, right? So the reason why is, say we have an array like this, and we landed here on the leftmost element. Now, we can't check mid -1. This will cause a emergency stop in the code because there's nothing to the left of it anymore. In an OR statement, the rest of the statement will only run if this returns false. So since over here, for middle index equals 0, this is true. This part of the statement won't run. And since this is true, we're at the leftmost number, and that number equals target, we return the leftmost target. Now let's take a look at the binary for rightmost bound. This is essentially exactly the same. Besides the middle statement, in fact, you can probably group these two functions together by some sort of if statement, depending if you want left or right. But to showcase this question, I'm going to separate them into two different functions. Similar logic, except we want to find the rightmost bound, right? So we check if the number equals to the target, say if we're over here, right? The number equals to the target, yes. Okay, so if middle equals len nums -1, so this checks if we're currently at the rightmost number in the array or not. If not, because we're over here, we check if nums middle +1, so nums middle +1 doesn't equal to the target. Over here, we see that +1 equals to the target, so this statement won't run. Instead of returning the middle index, what we need to do is to search on the right side of the array, right? So that's what you see here. When it's smaller than or equal to, you see the modification here. Before it was just smaller than. So if the number is smaller than or equal to, we want to move the left index I to middle +1. So this way we're researching through the right side of the array. And that's it. That's the algorithm for finding the left bound and the right bound. Just to repeat the difference, instead of just checking if the current middle is equal to the target, we check for left bound if there's anything on the left. If there's the same number on the left, obviously it's not the left bound, right? But if it's a different number on the left, we know that currently we're on the leftmost number. Similarly, on the right, if there's something on the right to the middle that equals to the target, then we know that, hey, this number is not the right bound. We want to search the rest of the right side of the array. If we are at the right side of the array and we see that the number on the right is a different number, or we are at the edge, we know that this is the rightmost target. So interestingly, if you go to the solutions section, right, you'll see a bunch of people writing binary search with only two cases in their if statement. They only have go right or go left. They don't have the check if current value equals target. This is actually the reason why I created this binary search video, because I want to dig through why it's so complicated to write binary search and why there's so many different ways of writing binary search and who was right. Okay, let me explain all of that to you. Originally, there's only one proper way of writing binary search, and that is with 3 checks. If the current number is smaller than the target, right, then we need to check through the right side of the array. If the current number is bigger than our target, right, then we need to check through the left side of the array. And if our current number equals to the target, right, then we return our current index. Easy peasy. However, this guy, whose name I will not try to pronounce, decided to merge the check target step with one of the going left or going right depending on the situation in 1962. So in his version of writing binary search, there's only 2 checks. You either go left or you go right. To make the situation even more confusing, depending if you want to find the right bound, okay, right bound, or you want to find the left bound, okay, leftmost, the way you write it is different. You use floor in leftmost, you use ceiling in rightmost, and over here you see how we assign going to left or right? That is also different too. Instead of both sides doing m+1 or m-1, depending on the situation, one side does m, one side does m-1, one side does m, one side does m+1. The good news is you do not need to learn this. You do not need to learn the alternatives. The proper way, or what I like to call proper way, the original way of writing binary search with all 3 checks cover both left bound, right bound, and no duplicates. So this binary search will carry through all your interviews, all your questions that you ever need. However, for the sake of science, I will explain the alternative procedures. Now, you might want to skip to the example question where I solve some of the more complicated questions. But I also want to clarify why the alternative procedures exist. The alternative procedures exist because sometimes when we want to check left bound and right bound, you're already seeing how long the if statement can get, right? In more complicated question, the if statement for checking if we're left bound or right bound can get even longer. In this case, writing it with this German man's approach, skipping the target check, will actually make your code cleaner or simplified. Except it also makes it very hard to understand why it works. Let's start a way of writing binary search where you will always find the left bound without the checking target. Okay? Just to be clear, there's actually multiple ways of doing these. This is just one setup that is easiest to memorize for me. So in this case, instead of doing a while loop for left smaller than or equal to right, just do left smaller than right. We don't need the equal case because by then we already found the answer. There's no equal check over here anyways. The important part to remember is about the index of finding middle, okay? I didn't explain this earlier, but there's a rounding error that comes with doing indexes. Say if we have a even number of indices, 0, 1, 2, 3, right? Left is 0, right is 3. If we do 0 plus 3 divided by 2 to find the middle, we can see that it equals 1.5. However, index need to be an integer, so you can't just have 1.5 index. That doesn't make sense. The floor of 1.5 is 1. The ceiling of 1.5 is 2. For finding the leftmost bound, you want to use math.floor of the index, so 1. So when we found the middle, floor will always give you the index that is immediately smaller than the middle, because the middle is a fraction. Floor will give you the index that is immediately smaller. Just imagine, since you're finding the left bound, you want to use the index that is smaller, okay? What the if statement is doing is that it combines the equal and the greater than case. So for the greater than case, if the current number, right, 3, is greater than the target, then we must go to the left side. If we equal to the target, we still want to go to the left side because there can be another number that equals to the target on the left side. Let me preface that this is just one way to set this up. I have seen some people do this instead, okay? But for me, I just do it this way so I know this works and it's easier for me to memorize. because if you mess up the one-off error, it will cause the program to run in a loop infinitely, and that's the last thing you want to do. How we make sense of this is by thinking that we merge the target check with going to the left side of the array. What this is essentially doing is that we keep on going to the left side of the array until we find our target. The reason why we set it to mid instead of mid -1 is because when we set it to r to mid, right, we're going to the left side of the array. It's still possible that the number we're currently on is the leftmost bound, so we would like to include it in our next search. Say if we're over here, right, and we want to go left again. If we did not include our current number, then we would search just 1. But since we include our current number, we search 2 and 1. In this case, we can find out that 2 is our target, leftmost bound. On the other hand, if our current number is smaller than the target, then we would want to go to the right. So we set our left bound to middle +1. The reason is because this case covers when the index number equals to target already. So here we don't need to check mid, we just need to check middle +1. Alright, let's do the right bound example, which is the third way of writing binary search. Once again, we have our while loop to run while left is smaller than r. There's no need for smaller than equal to because the equal case is covered. In here, when we calculate the middle, we want the ceiling. So say if we have even number, the index would be 1.5, but since index has to be an integer, ceiling will give 2. Think about it this way. When we want the right bound, we want the index that is on the right side, which is ceiling. When we want to find the left bound, we want the index that's on the left side. That's why we use floor. Easy peasy. As you can see here, the if statement is completely different or entirely opposite. I intentionally engineered it this way so it's easier to memorize. You just do the opposite thing. What we're doing here is that, hey, we find the middle, right? So middle to the right, because we're trying to find the right bound. If this number is smaller or equal to the target is 2, this number equals, so we want L, the left bound, to become the middle index over here. If the number is bigger than the target, so here if imagine this is like 3, right, and this is 2, then in this case we want to go to the left side, and since we already confirmed this does not equal to the target, it's safe to do middle -1, exclude the number we're currently at. So once again, if our current number we are on is smaller than or equal to the target, right, we want to go to the right. And we set L equal to the middle because it's possible that this number is the target, right? So we want to go to the right. And if this current number is too big, then we want to go to the left. And since we already covered the equal case, we do the -1. As you can see, this rate of writing binary search is actually a little bit faster just because you skip an if statement case. But I highly recommend using the first way of writing binary search with the checking the target, checking left, checking right. The reason is that logic is a lot easier to memorize and makes more intuitive sense. And the other thing is the original way of writing it with the middle check can cover left bound, right bound as well. So there's really no reason for you to risk writing this way and making it wrong. Alright, let's do a more complicated question here. So over here we want to design a time-based key value store. Design a time-based key value store data structure that can store multiple values for the same key at different timestamp and retrieve the key's value at a certain timestamp. It sounds complicated. Timestamp initializes the object of the data structure, set. So here we want to set key, value, timestamp, string, get. So here we want to get using the key and the timestamp. So returns the value that was set, that was called previously with timestamp previously smaller or equal to the timestamp we requested. If there are multiple such values, we return the value associated with the largest timestamp previous. If there are no such value, we return nothing. So over here, let's see, time, set. So here we initialize our time map. Here we set key, foo, value bar, timestamp 1, right? So if here we call get, key is foo, value timestamp is 1, so we want all the entry where key is foo and timestamp is smaller or equal to 1. So there's only one entry. Thus we return bar. We call get again with foo, so that's the key, timestamp. So since 1 is smaller than 3, we return bar again. Now, we do another set with key foo, so same key, but different value, bar 2, right, with timestamp 4. Now when we call get, same key, right, foo, and we want 4. Since there are 2 entries here, 1, 2, we see that the most recent value of timestamp that's smaller or equal to 4 is bar 2, right? So we return bar 2. Next, we search foo, so key is foo, timestamp is 5. 4 is smaller than 5, it's the most recent one. We return bar 2 again. Yeah, this sounds a little bit complicated, but it's not. So over here, we can't just use a simple dictionary because instead of just key and value, we have key, value, and timestamp. What we can do is design a dictionary that has key as the key, but inside we have an array of value with their timestamp. The structure looks something like this. We use a default dict of list. So we have a dictionary where we have the key and a list of value with their timestamp in a tuple. So in this case, if say someone comes and search for timestamp 4, right, then we will return this. Someone search for timestamp 6, we can return this. Timestamp 1, we can return this. How does this relate to binary search? Well, you see here we got an array with an increasing number of timestamp, and we need to search for a certain timestamp. This is the perfect use case for using binary search to speed up the lookup of the get function. For the set function, we simply store into our dictionary key, find the array, and append a pair of value and timestamp. This is exactly how I taught you binary search earlier. First, we get our array by using the key. Next, we set up the left index, right index. And while the left index is smaller than or equal to the right index, right, we find our middle index and check if the middle index timestamp equals our target timestamp. If it is, we return our value. If the timestamp is smaller than our target timestamp, then we got to go to the right side of the array. Hence, we set left to be middle plus 1. Otherwise, the timestamp is on the left side of array, so we set the right index to middle minus 1, right? Funny enough, if you submit this, it doesn't actually work. Reason being is that this, we're checking strictly if the timestamp equals. But for this question, say if someone searches foo3 and we have timestamp 1, this should also constitute as a match. So we got to check not just equal, but the first instance that is smaller than or equal to our timestamp. Alright, here's our monstrous if statement. So we check if our current target is equals to the timestamp, right? Say if our target is 4 and we match with 4, then we return our current index. Done. What if the target is 7, right? So 7 is greater than anything in the element. In this case, we check that our current timestamp is smaller than the target timestamp, 6 is smaller than 7, and our current index is equal to the rightmost bound. So over here, our current index is equal to the rightmost bound. There's nothing on the left. In this case, this will be the biggest element that is smaller than the target timestamp. Another case can be, say if our target is 5, right? Target is 5, so somewhere in between here. The biggest timestamp smaller than 5 is 4. In this case, we see that, hey, it does not equal to the target timestamp, right? 4 does not equal to 5, but our current timestamp, 4, is smaller than the target timestamp. In addition, the timestamp next to it on the right, plus 1, is greater than the target timestamp. So the smallest timestamp is 4. So the biggest timestamp that is smaller than 5 is 4. Alright, I'm going to ask you a follow-up question. What happens if we allow duplicates? So say we have timestamp 6, we have another timestamp 6, but their values are different. And in this case, we want the most recent entry. This is a very realistic use case. Say if you have a database and you're going through all the data, right? It's totally possible that second differentiation is not good enough for the amount of data coming in. So you will get multiple entries on the same second. In this case, you want the most recent entry. So what will you do? We would modify the if statement so that we check, hey, is our current timestamp smaller than the target, or our current timestamp equal to the target? In addition, we are either at the end of the array, or the array number next to us is greater than the timestamp. That is when we return a match. So in this case, if we simply have a match, since the number next to us is not greater than the timestamp, we would keep on searching. Another way of solving this, even with the duplicate, is to use the rightmost bound method of writing binary search. This is why you see some people like to use the rightmost bound method or the leftmost bound method. The reason is it's a lot shorter. You don't have to deal with the complicated if statement. All you have to do is memorize the formula, make sure you don't go into the infinite loop, and since you're confident and you know that this will give you the rightmost target and the binary search works, it's a lot less code. But then again, this is very memorize the formula. So if you memorize it wrong or the situation changes a little, it's harder to adapt, right? Let's try a different question. This question is called find peak element. It's a classic. A peak element is an element that is strictly greater than its neighbors. Given a zero index integer array nums, find a peak element, blah, blah, blah. Let me explain what this means, okay? What a peak element is like 3. 3 is greater than elements on its left, greater than element on the right. So that's a peak element. Over here, we have a bunch of numbers, and there are multiple peak elements. So 6 is a peak element, greater than left and right, and 2 is a peak element, greater than left and right. 3 is not, because 3, although greater than 1, is less than 5. Alright, you might be thinking here, how does this relate remotely to binary search? Because with binary search, you need a sorted array, right? Over here, we have a bunch of numbers, and they're not sorted at all. The way I like to think of it is like, imagine you have a bunch of smaller sorted array, right? So think of it as 1 to 2 is a sorted array, 1, 3, 5, 6 is a sorted array. You just need to find the end of the sorted array for one of them. This is why, even though the entire array is not sorted, since part of it is sorted, binary search still works. The official solution has a different explanation. It basically separates it into 3 cases. In case 1, we have a decreasing array. Peak is here, then it gets lower and lower. In this case, say if we start with the middle with binary search. We know it's not here, we know it's not here, and finally we find the peak. Each time cutting the search space by half, right? In another case, say we have increasing amount of numbers. Once again, binary search, we find a middle, we know it's not on this half, middle, not on this half, middle, finally find our result. Each time reducing the space by half. What if we have the peak somewhere in the middle, right? So say we use binary search. We find a middle, we know it's not on this half. We find the middle, we know it's this, because it's not on this half either. The basis of this explanation is saying that there's only 3 possible ways a peak can exist, either on a decreasing order, an increasing order, or somewhere in the middle. In all of these cases, binary search, you're able to find the peak. Here's my solution using the 3 check method or the check middle method, right? Again, we set up left bound, right bound, and then we run our while loop while I is smaller or equal than the left bound. We find our middle and we check. If the left side is smaller and the right side is smaller, we know we are at the middle. Otherwise, if the left side is smaller, we would then go to the right. If the right side is smaller, we will go to the left. We keep on heading toward the side that is bigger until we find the peak. What I've basically done is separate the big if statement into 2 smaller pieces and combining them with an AND operator. Is left smaller checks if the left side is smaller or not. If right side smaller is checking if the right side is smaller or not. There's basically 2 cases for if left side is small, right? Either we're on the very edge, so say we are here. There's nothing on the left. Middle equals 0, we're over here, nothing on the left. By default, the left side is smaller than us. Otherwise, say there's something on the left. We check if that something is smaller than us. If that something is smaller than us, then we know that the left side number is smaller than us. Is right side smaller? Same logic, reversed, right? If we're at the rightmost number, then by default, since nothing is there, the right side is smaller than us. If we have something on the right, we check, hey, is 1 smaller than 3? Yes, the number directly on the right is smaller than us currently. The reason why I like this method of writing binary search is because the logic is clear. Either we are at the peak where both left and right is smaller than us. Clearly this is the target, we return the target, right? Or currently the left side, say we're over here, right, on 3. It's clear to us that the left side is smaller, so we want to go to the right side. Otherwise, say we're on this if statement and we are at 2. Clearly the right side is smaller, we want to go to the left side. Everything is clear and you understand what is going on. Obviously, you can still use the simplified version with no middle check. All you have to do is, hey, check if left bound is smaller. If left bound is smaller, we will go to the right. If the right side is smaller, we go to the left. Here we have the right bound method, just because I remember it better. You can also use the left bound method. Since we no longer check this, we only make one check, we can delete this. So you can see the function is a lot simpler and it's also accepted. It's just like when someone asks you this question, it's hard to think of the solution intuitively. Alright, just when you think you understand everything, let's do a weird and complicated question. This one is called find peak element 2. It's basically the same as find peak element, except it's on a 2D plane. You can see here 30 is a peak because it's greater than all of the numbers top, down, left, right. 10 is not a peak because it's smaller than right and smaller than left. 16, not a peak, smaller than up and smaller than right. One way to approach this question is by doing the following, right? You can run a binary search on every row. We run a binary search on the first row. We find 20. Is 20 the peak element? We check. Top, down? No. 30 is bigger than 20. Alright, we run binary search on the next row. Let's see, we land on 30. Is 30 a peak element? Yes, 30 is a peak element because it's bigger than top, down. This algorithm actually doesn't work. Say if we have a 2D array like this, right? We will go through the first row, we find a peak. Since there's only one peak, it's 50. 50 is smaller than 500, no good. Second row, there's 2 peaks, 3 and 500. If we landed on 3 as the peak for this 1D array, we can see that 3 is smaller than 30, that's no good. However, there's actually another peak over here, 500. Instead, here's what we need to do, okay? Here's what we need to do. We're still doing a find peak, like the original algorithm, checking if left is smaller or right is smaller. We're still doing binary search from left to right, okay? Except each time, after we find the middle element, so say if it's 10, 20, 15, right? The middle element is 20. What we're gonna do is we're gonna find the maximum number on this column. Here, the maximum number is 30, okay? Since it's 30, and then we're gonna check if left is smaller and if right is smaller. If both is smaller, then we found a peak and we return the result. Alright, let's go through the example that we couldn't solve earlier, right? So first, we're still doing left to right. We get our middle index, which is at 40. 42, right? On this column, we find the maximum element, which is 40. We check if left is smaller, left is smaller. If right is smaller, right is not smaller. So here, what we need to do is we check, okay, so right is not smaller, and then we need to go towards the right. So we're over here. We're gonna still run our binary search left and right. Since we're doing a floor operation, it will be on this column. We find the max of this column, which is 500. We check if left is smaller, yes, left is smaller. Right is smaller, right is smaller. So here, we find our peak. Let's talk about the runtime. Say if the grid is made out of n times m number of elements, right? and we're doing binary search on the m direction, so we have log m. We're doing iterative search for the max on the n direction each time we run binary search, so we have n times log m as our runtime. I want to highlight some special part about the code. Overall, this is basically just find peak element. As you can see here, we find mid, we get its left smaller, its right smaller, same thing exactly. The only difference is in the middle, we're going to search through every single element on the current column to find the max column element. I actually don't know how to mathematically explain the solution to prove that it's correct. However, I like to think about it this way. When you are doing binary search, you're not just finding the peak on the current row. That's not what you're doing, right? What you're doing is trying to find the peak column. What I mean by finding the peak column is that here's what we're doing, okay? Every time, every iteration of the binary search, we find the maximum of the current column. What this means is instead of viewing it as a 2D array, we're essentially only processing binary search on 21, 30, 32. In this case, we can just use our find peak element algorithm from our previous question. Yeah, that's how this works. That is the end of the video. I hope you were able to understand binary search a lot better. I used to just simply memorize the binary search algorithm, and I never understood why there's so many different variations, why no one seems to agree on how to write a binary search properly. Now I understand. There's actually multiple ways of writing binary search, and there's a lot of alternatives, pros and cons of using those alternatives. Honestly, the series serves more as a note to myself, but I'm glad you're able to watch this, and hopefully you learned something too. See you next time. Bye.